Sorry about the delay. So this talk will be talking about Magnolify, and it will be co-presented by me and my coworker Claire. So let's just get started. Yeah, a little bit about us. Both of us are data infrastructure engineers at Spotify, and we use Scala mainly for data processing. So we have a couple of libraries open source for like data
Neville,
pipelining.
the layout is weird. I've got your notes on half the screen. I don't know if that's intentional. Sorry. There you go.
Wait, was that a present? Oh, so I can't have my presenter notes. All right, then I'll just use this one. Is the layout good?
Yes.
Right now? Okay, cool. So yeah, so both of us are data infrastructure engineer at Spotify. We use Scala mainly for data processing. We have a couple of open source libraries for data pipelines and machine learning, that sort of stuff. Some stats, yada yada. We probably, I think it's been confirmed that we have the largest Google Cloud data flow job in existence. And we also participate in some open source community like around the Scala Center advisory board, and we contribute and co-maintain some of the Twitter libraries for data processing. Anyway, let's get started. So a brief agenda of today, and we'll be talking about type classes and how to derive them with Magnolia. We'll be looking at some instances in Scala check and cats particularly. And after that, we'll be testing them with property-based testing using Scala check and discipline. And after that, Claire will talk about the data type converters, which are also type classes. And we'll wrap up with a comparison of Magnolia versus shapeless approach for type class derivation and some other fun, interesting bits. All right, let's get started. So, I mean, this is a type level conference, so I hope most of you are familiar with type classes. It's a type system construct that supports parametric polymorphism. And the most common and basic ones are like cases like show. So for arbitrary type of T, we can display pretty print a string here. And in Scala, we often have a companion object with like syntactic sugars, implicit instances, and so on and so forth. Semigroup is another very common type class, especially in the data processing world, basically algebraic structure that over set has a binary associative operation. For example, integers and a plus, or sets and a union, those are semigroups. And of course, we can have also have a companion object here with some syntactic sugar and helper methods. So how do we do type class derivation? So first, let's take a look at the case of show. We can have some primitive instances for show of string or int, and those are very trivial, just convert it to a string. And then we can do that using an implicit diff for like tuple2s, just using implicit arguments to summon the implicit fields for like the A and B, the two fields. And then we can compose them into a show for tuple2, any tuple2 where A and B, the type of A and B have implicits defined. So this works, and we can, by extension, do that for tuple 3, 4, 5, all the way up to 22. It's pretty straightforward. Obviously, the downside is it only works for tuples, doesn't work for case class, you have to handcrop them, and no CO traits either, like no ADTs. So Magnolia is a way for deriving such type classes. They compile time using macros, and it works for both case classes or products and CO traits co-products. And it's written by John Pretty, and we actually use it pretty heavily in production in a lot of the heavy data pipelines. So we'll be taking a closer look at Magnolia and how to use that to derive type classes. So back to the show again, this is the Magnolia example of deriving show using its API. And basically we start with the object of show derivation. First we alias the type class we want to derive to type class T. And this is the type class in question is show. And it has two methods, combine and dispatch. Combine is for combining the fields of a case class into a composed type class. And dispatch is for ADTs or CO traits. So from a root, let's say a shape, to dispatch it to one of the subtypes, for example, a point, rectangle, or circle. And at last, we have an implicit method to summon this derivation macro in Magnolia. So let's take a closer look at the two methods, combine and dispatch, and all the parameters in question here. So for combine, let's take a look at an example for a simple case class of record with two fields, S of string and I of T. So what happens here is Magnolia analyzes the structure and then provides the case class type parameter to our combine method, which describes the record that we want to derive and also the type class. And if we take a closer look at the case class type here, and it has obviously a type name, that's record, and a list of parameters, each one of those representing a field in our case class, like S of string and I of t. And for each of these parameters, we have a dependent p type, which describes the actual field type, like string or int, a label, that's a stringly typed label, that's the field name, a type class, which is summoned implicitly through the search scope. So show of string or the show of int, as we've seen in the previous slide in the companion object. And then at last is the dereference method, which is basically a getter. So from the original type of record, how to get a field of S or field of I. So it's pretty straightforward. By doing this, we can derive type classes of show for basically any case class. And the next one, let's take a look at the seal trait. So again, back to a very typical example of a shape. So our seal trait, the root class is root type is shape, and we have two implementations, a point and a rectangle, the two subtypes. So for Magnolia to work, it supplies us with a seal trait type, which describes the structure of this hierarchy. And then we implement some methods. So digging into seal trait, we can see the same variables like type class for show, type for our shape, the root type, obviously the type name, and the dispatch method. So we can pass in the root type, a shape, which it will be dispatched to the correct subtype, either a point or rectangle in this case. And because a point and rectangle are case classes, they are already derived by the combine method in the previous slide. And if we take a closer look at the subtype, there's a type class, which again is the implicit type class show of either point or rectangle, one of the subtypes, and also a partial function that casts the supertype shape to either one of them. All right, so given these tools, now let's try to derive some interesting things. We'll start with a Scala check, which is a property-based testing library, and it's built around this concept of deterministic generators, which sort of looks like this: a generator of arbitrary type T, like an integer, string, a list, or even tuples. So given some parameters in the random seed, it will be able to produce an option of T, a random value. It has map and flat map methods for composing generators. And in Scala check, generators are wrapped in this type arbitrary, which has a lot of implicit instances. So arbitrary of string, int, list, so on and so forth. These are provided by the library. So how do we derive a generator for a record in this case? First, we have to summon, without Magnolia, first we have to summon the implicits for generator of individual fields, string and int. And then we can do the flat map and map check. It sort of looks like this. And this looks familiar, right? This is a monad. So we can do the for yield comprehension as well to get a generator of record. And you wrap that in arbitrary of record. Here we go. That's the arbitrary of record that we want. And we can sort of replicate the same logic, but more generically to any case class and ADTs using Magnolia. And an interesting fact here is that generators in Scala check are actually state monads. What we don't see here from the user API is that every time the generator produces a record, it takes in a seed as input, produces the value T, and the next seed to be passed into the next generation. And that's how it handles like deterministic generation of a sequence or complex records. And there's an excellent blog post that you can check out later. All right, so let's see how this works with Magnolia. So first we alias type class to arbitrary, and then we define the two methods, combine and dispatch. And it's super straightforward because we already knew that a generator gen T is a monad. We can use case class.construct monadic to do that automatically. And all we need to do is supply the fact that arbitrary is a monad and adapt to monad gen, which I'm going to show in a minute. And for the seal traits, it's very similar. For supertype, we just want to randomly generate either one of the subtypes, hence the gen one of and the subtypes arbitrary instances. And the monadic gen is just adapted to Magnolia's monadic type class. So it has point, flat map, and map, the three standard methods in a typical monad. So moving on, let's try to test this arbitrary. So how do we test a random generator? There's some property. It's a perfect case for property-based testing. So given some default parameters in the generator, what should we look for if it behaves correctly or not? The first one is uniqueness. So given a predetermined seed, if we generate 10 instances of the record, they should be like somewhat different, right? Like there should be more than one different unique instances. And some of you might question why is it greater than 1 not to set our size equal to 10? There are cases where it's just impossible. The sample size is just not that great. For example, a gen of Boolean can only have 2 possible outcomes, true or false. A gen of option of Boolean can only have 3 outcomes. So this is the first property we want to test. And the second property, we want the generators to be deterministic, which means that given the same input seed, we should be able to generate the same record or value. So generator passed in same parameter, same seed should be equal. All right, let's run this. Oops, Stack Overflow error. So what happened there? If we looked a little further, in my test cases, I actually have a recursive ADT, like a typical binary tree, a root type of node with 2 subtypes, leaf or branch, and then branch recurs itself. So there's a pretty good chance that the branch will just keep on recursing until we blow up the stack space. So how do we fix this? It turns out that Scala check generators has an internal attribute called size, and then used by a lot of built-in generators. For example, a generator of a list actually will rely on the size to make sure it doesn't generate infinite amount of elements and then blow up memory. And in this case, we can leverage that size attribute. And for each generation, we just shrink the size by 1. And once we run out of size, in the else case, we return a generator failure. So this should fix our problem, right? Let's run a test again. It failed again. It turns out it's better this time, no stack overflow, but it failed the uniqueness property because for some cases, it failed to generate enough unique values. And remember our unique property test if the generated values to set or size greater than 1. And in this case, it's actually empty. And it turns out because when generators fail, the generator produces none, and the list of generators uses traverse internally and it will produce a nil. And all of this is because the Magnolia derived generators here are not aware of the structure of our ADT. It doesn't know that the fact that branch will keep recursing, whereas leaf is the terminal state. And we actually, in this case, wanted to fall back to leaf instead of fail, right? When run out of size. And it turns out there's a solution already in another similar library by Alex Aschebaum, Scala check shapeless, which is very similar to our approach, but using shapeless for deriving arbitrary instances. So it introduces this fallback type class and has a default value which just returns gen fail. And we as users can inject alternative fallback value that will not fail and provide a graceful terminal condition. And the fix is actually pretty simple. We add this type class as a context bomb. And in the else branch, we summon the implicit fallback and just retrieve the value. And to use this, we can just introduce implicit value of fallback for the case of binary tree with fallback to the leaf and not a branch. And this will terminate the recursion gracefully. All right, this fixed it. And then the next, let's move on to magnolify some cats. So first we look at the cats equal type class, which basically implements a method to check if 2 values are equivalent or equal. And the combine method is super straightforward. For 2 case classes to be equal, every field needs to be equal. So we just do a for all over all the parameters and delegate to the field type class of equal. And dispatch is similar. So to check whether two CO traits X and Y are equal, we first dispatch to X subtype. And remember that sub.cast is a partial function. So we check that if X subtype is defined for Y as well, basically meaning if X and Y are of the same subtype. And if that's the case, we delegate to the subtypes type class equivalent to check the two values, X and Y. And we can do that for semigroup as well. Semigroup is basically a combine of values like sum for int and union for set. And semigroup for records, basically just a field level, like per column-wise semigroup application. And we can, again, delegate to the field, the p.type class to combine each individual fields. And the dispatch case actually doesn't make sense for semigroup. Like, it doesn't make sense to sum like a point or circle or rectangle because they are of different types, and logically it doesn't make sense. And one of my coworker, Andrew Martin, actually came up with this trick, basically introducing a type class with no instance. And by doing that, we can fail gracefully with a compilation error instead of a runtime not implemented error. So this is how we handle a lot of cases where like CO traits makes no sense for the particular type class. So all of this works pretty nicely, and we want to test them. It turns out that CATS already includes a library called Discipline, which includes Scala check properties, or also known as laws for the most common type classes like eco, semigroup, monoid, and monads. So we can reuse that without handcrafting our own rules. So for example, for eco of records, we can just use discipline eco test and then implement the 4 rules: reflexivity, symmetry, anti-symmetry, and transitivity. And then for semigroup, similarly, it checks the property that semigroups needs to be associative. The repeated and or combine and methods need to be behave the same in the same way as combine. Also, combine option is just normally implemented as a reduction using the combine method. All right. So if we pay closer attention to the anti-symmetry law for eco, it requires a f of t to t, a function from t to t. And the law says if two values x and y are equivalent, f of x and f of y should be equivalent, right? So if 1 equals to 1, then 1 plus 10 should be equal to 1 plus 10. And to do that, we need an implicit instance of arbitrary from t to t. And note that this is different from arbitrary of t, which is just random generator for t. This is generating a function that takes a t as input, returns a t. Like you can imagine like arbitrary of x int equals to x plus 1 is not the same as just randomly generate an int. And to do that, turns out Scala check already has an implicit def to produce arbitrary functions, but it requires not only just the output arbitrary for z, from A to Z, it also requires for the input type A, a Cogen type for A. So what is this Cogen? And if we take a closer look, it turns out Cogen has a method. It's a trait with a method called perturb that takes a seed and the value returns another seed. And there's a definition from some internet dictionary, but we're not going to get into the detail. But this looks familiar, actually. Remember the gen that we talked about in one of the previous slides about gen being a state monad. If we compare the signature, gen takes a seed as a state monad, takes a seed as a state, produce a value, and then produce the next seed to be passed along the next gen invocation. And Cogen looks like the inverse of gen, which takes a seed and the current value and produce the previous seed. And there's actually an excellent talk from Eric Rosheim on functions of determinism in property-based testing. It digs into this particular topic in depth. It's really worth checking out. So now we know these properties. These are gen and Cogen turns out to be very similar, just the inverse of each other. So we can implement Cogen with Magnolia. And the combine method turns out to be just chaining the seed using a fold left over all the parameters. And then for each parameter, we call the perturb pass in the seed and the value of the current field. And dispatch similarly, given a root type, we dispatch to the subtype and delegate the perturb to the subtype's type class. So this should work, right? So let's test it. How do we test it? Remember the arbitrary properties, the uniqueness and consistency. We can implement that similarly for Cogen. So uniqueness for Cogen requires us for the same seed, generating a list of objects, and then calling perturb on these unique objects should produce the same unique number of unique or previous seeds. Hence the uniqueness requirement. And for the consistency one, for the same seed and same input, perturb should produce the same previous seed. It looks nice and fine, so let's try to run this test. Oops, actually failed for one of the test cases, nullable, which is a case class I defined. Okay, so let's take a closer look. Why did it fail? Turns out the case class has 3 fields: option of Boolean, option of int, and option of string. And let's look at how they're implementing Scala check. The Cogen for these 3 types, for option of anything, it's actually using o.fold, which means it's a no op for none. And only if it's a sum, it delegates to the inner type base Cogen. And for Boolean, it's actually implemented the same way as an integer of 1 or 0. And so in this case, the sum of false and sum of 0 are the same. And the other 2 options, the 2 nons, are basically bypassed by the Cogen. Hence, these two case classes produce the same value for Cogen. To recap, yeah, none causes a no op, Boolean behaves the same as an integer. So we can fix that by injecting the position, because the 3 fields actually should be treated differently. And luckily, we can retrieve that using the parameter.index, which tells us the position in the case class. So by injecting that integer Cogen, we fix the test and it works. All right, so moving on to the next. There's one more very subtle bug. It's a flaky bug that happens once in a while. And when it fails, Scala check will actually tell me the random seed that causes the failure. And it always looks very weird, like all A. It looks weird for doesn't look very random to me. And upon a little bit further digging, it turns out when this seed happens, the seed always produces itself. Basically, no matter how many times seed.next I call, it always produces the same value, which also means that it's impossible to generate anything unique. It will always generate the same values over and over again. And that causes all my uniqueness tests to fail. So what happens here? And it turns out that my property test written as prop for all given the seed, which requires an implicit arbitrary instance for seed. And when I dig into Scala check, there's actually no implementation of arbitrary seed. So where does that came from? So we look into the seed implementation. Obviously, it has a next method which returns the next seed by mangling some bits internally. And seed itself uses 4 longs to represent the random seed. And of course, a factoring method that takes a single long. And after a little bit more digging, I realized that if I pass in 4 zeros for the internal state of the seed, that reproduces the magical seed that's causing the problem. That's the all A's seed, and that's actually causing the problem. So who generated that? And turns out because of the case class apply, Magnolia kicks in and actually provides the implicit instance for the seed. And there's actually a condition where Magnolia can Scala check long generators can generate like 4 zeros in a row, and that causes the seed that never produce any unique elements. So the fix is actually really simple. I'll just replace the seed with the single long and derive the seed with that. And another fix I did is to improve the import mechanism of the library. So I can have like auto, implicit derivation, and the semi-auto. So the semi-auto requires the user to import the derivation object and then call the derivation method explicitly, whereas the other one just imports everything. And I think this is a common technique used by a lot of similar libraries, like Serzi does something similar as well. All right, so next I'll move on and pass to my coworker Claire to talk about all the data generators.
Hey, can you guys hear me?
Yes.
Yeah, okay, great. Share my screen. I think I want this guy. Okay. Okay, hey, so I'm Claire. I'm going to be talking a little bit about the data type converters that we've implemented in Magnolify. Right, so what do I mean by data type converters? So we're Scala developers. We generally like to work with case classes. They're lightweight and they're easy to use. But if your Scala program has any sort of I/O component, the data that you're reading and writing is going to be deserialized into some underlying data type, one that might be hard to work with, or it's space inefficient, or it doesn't play well with your Scala library functions. So we have implemented a series of Magnolia derived converters between Scala case classes and these underlying serialization formats, so that your Scala I/O operations feel like you're just seamlessly reading and writing case classes. So some of the examples of the converters that we've implemented, we've done converters for BigQuery, JDastore. These are all Google Cloud products that we use pretty heavily at Spotify, which is why we picked them. Protobuf, TensorFlow, and Avro. And I'm going to go into a little bit more depth on Avro in a bit. Right, so in Magnolify, we've defined this converter trait. As you can see, it has a from and a to method, which is pretty expected for a converter. But the strange thing is that it actually has 3 type parameters, which you may not expect. So T would be the type of your case class that you'd like to derive a converter for. But the reader and writer types are a little bit more complex. They both refer to the deserialized data representation, but the reader type represents the data as it is read from binary into the format, whereas the writer type represents the data that you can actually write to. So most of the time these are the same, but there are a few exceptions, and I'll give an example in a couple slides. So I'm going to go into the Avro converter, Avro type. Right, so you guys are maybe familiar with the Avro Java library, but if not, here's a snippet of the main interface that all Avro classes have to implement. As you can see, it pretty much behaves like a map. So there's a default implementation for a generic record, this record class above. It keeps track of keys and values using 2 objects, a schema and an array of objects. So you can see the schema class below. It contains information about the type of the Avro object, whether it's a primitive field like an integer, a complex one like a map or a list, or it is a generic record, the record type. And the field class contains some metadata about the field, like the name, the default value, the documentation. So this record implementation uses the information from schema to keep track of where the value corresponding to each key is indexed in this values list. So back to our Avro type converter, we have this basic trait, Avro field, that can be used to represent any Avro type, whether it's a record or a primitive field. You can see that it has a schema, a default value, and these from and to converters. The reason that we had to add this from any method at the bottom is because, as you saw on the previous slide, the get method of generic record returns an object. And we know what the underlying class is going to be, so we do have to cast it, which is unfortunate, but it's Avro. Right, and we can use this Avro field to implement our converter from case class to generic record. So it's constructed, as you can see, using an implicit Avro field from T to generic record. And that's implicitly summoned. And the reader and writer types are here, are both generic record. Yeah, so we leave the case class derivation to Magnolia. I'll go into that on the next slide, but for now I'm going to talk about how we kind of explicitly enumerate the conversions for all these primitive and complex types. Some of them are really simple. For example, int here, an int is just an int, whether it's in Scala or Avro. You can see it's just an identity function. But for string, we actually see a case where the reader and the writer type are different. So Avro by default stores strings as UTF-8 under the hood, but the Avro Java API will actually return a char sequence, which you can't just cast to a string. However, when it comes to writing, people just want to work with strings, and string implements char sequence. So that's why it's the writer type. And here you see the converter for an option. It takes an implicit Avro field of the underlying type T. And I'm just showing the schema derivation. It creates a union type of null and the underlying type classes schema. Okay, so I wanted to show briefly what our Magnolia derivation code looks like. Neville did talk about combine and dispatch, so I won't go into too much depth on those. You can see that the reader and writer types are both generic record, and the conversion happens using the implicit type classes of each field to convert them to and from their underlying Avro types. And the reason we store schema as a string here is because as of Avro 1.8, schema is actually not serializable. It was made serializable in 1.9, but 1.8 is still very widely used. And if your Scala program is something like a MapReduce job, it may be important for your data types to survive closure. So we are storing it as a string, and the schema type on Avro can be easily parsed and written as a string, so it's no problem. And we did choose to not implement dispatch since a sealed trait doesn't have a clear representation in Avro. Maybe in the future we could think about supporting complex union types, but I'm not sure. Okay, so I'm going to show you pretty quickly how this works in action. So this is just on the REPL. First, you're going to import the Magnolify Avro package, which includes the implicits you need to create your converters. Then I define this very simple case class. It has 3 fields, an integer, a list of strings, and an optional Boolean. And I just construct an arbitrary instance of that. And then you can kind of summon your converter implicitly using this Avro type. And here's what happens when you use your converter to convert this instance of foo to Avro. It'll give you a generic record, and you can see that the map of values looks correct, and the schema is as we would expect. You can see for the optional Boolean, the schema is a union of null and Boolean, so that looks good. And when you convert back from generic record, you get the original foo object. So, okay, I'm gonna wrap it up and pretty briefly list the other converters we've implemented. So BigQuery works with table row. So we implemented a table row type. Protobuf has a message. TensorFlow has an example. Datastore has an entity. And yeah, that's it. I'm gonna give it back to Neville to talk a little bit about shapeless. Cool.
All right. Can you see the slides?
Yes.
Yeah. All right. Let me fast forward to the same point in the slides. Okay. Back. All right. So Magnolia is kind of like the new kids on the block. And before that, we've been using shapeless pretty heavily. And this is just a very simple comparison between the subset of features of shapeless, which does type class derivation, and how it compares to Magnolify. So before that, I actually tried to implement the same converters, the whole of all the various types Claire mentioned using shapeless. One of the biggest differences is that shapeless rely on implicits heavily and has these like compile time generated implicit type classes like label generic.aux, and a few are like value types that needs to be summoned via the implicit arguments. So the method signature for like shapeless based implementation is actually quite complex. So each method needs to have these implicit arguments and need to be propagated throughout your code chain and code stack. And it's, in my opinion, from a user experience level, it's less ideal, especially if someone needs to use your converter in a library or in the data pipeline, or needs to be like propagated all the way. And on top of that, because of the use of implicits and the problem with like divergent or ambiguous implicits, we end up with just for the example of the converters from the to and from, we end up with these low priority implicit chaining that's become pretty unwieldy, and it's pretty hard to maintain or read from a library maintainer point of view. So for this point, Magnolia is actually much simpler from a user experience aspect. And the next one, the benchmark. Because Magnolia doesn't rely on such implicit resolution during compile time, the compilation speed is actually order of magnitude better. And this is a very like unscientific comparison using handcrafted case classes. I think a couple of case classes with 50 or 100 fields each, and then you can already see the differences. And imagine some of data pipelines, we have dozens or even hundreds of case classes with lots of values and tuples and fields. And it becomes, they all add up pretty quickly. And in terms of performance, because both library does all the derivation and influence at compile time, the runtime performance is actually pretty comparable. Again, neither of these are like super heavily micro optimized, but the performance looks pretty good from our benchmarks. And moving on, the last slide, some interesting bits. As I mentioned, ambiguous implicit values has become a problem. And on top of that, some libraries also implement like conflicting implicits. For example, it turns out lists and options are actually CO traits. So Magnolia will kick in for these types and try to derive them using dispatch. And typical use cases for users who import cats.instance.all, and which also include like semigroup of lists and options, which conflicts actually with the Magnolify derived instances. So for those who actually have to do some trick to like override implicits or like some lower priority chaining to work around that. A fun observation, the hash testing discipline actually checks the hash behavior against the Scala hash methods, default Scala hash method, and Java universal hash. So we actually try to mimic that by using the same implementation in the Scala compiler. We've also done a little bit of micro optimization. Again, a lot of these type classes are heavily used in data pipeline in the very hot loop, so performance is actually pretty critical. For example, semigroup.combine option allows us to combine a sequence of objects by using some mutable data structure under the hood and avoid copying, and we actually optimize that. Unfortunately, we still have to maintain 2.11 compatibility because of some old data pipelines. So we have our own fork of Magnolia just for that. And also for 2.13, there's some breaking changes not really can build from. And you have to add some shins to work around that as well. And the last point, because everything needs to be run in a data pipeline in the distributed system, we need to make sure everything is serializable and not just like Java serializable. Some cases it need to be serialized using the particular data type serialization method. So those are the things we need to be particularly careful with and write a lot of tests to cover. But anyway, I think that's it, just to mention some related projects that you can check out. So Shio is our main data processing framework on top of Apache Beam and Google Cloud Data Flow, and then uses Magnolia heavily for deriving coders for serializing data. And that happens whenever data has to go through shuffle in the MapReduce processing. We actually managed to derive Magnolia type classes for Parquet Hadoop IO, so we can read and write case classes in Parquet, which is sort of vintage Hadoop era Java style. But it's possible to use Magnolia to derive this. And also shapeless is honorable mention. We use that heavily in the past, and there's some libraries that's worth checking out. And I think that's it. So again, everything here is part of the open source library, Magnolify, so you can check it out. Feel free to submit pull requests or reports. And I think that's it. We have had time for questions. Or...
Yeah, we have a little bit of time.
Okay.
There was a question in the chat.
Yeah, I need to check the Slack.
Oh no, it's in the Zoom chat.
Okay. Chat.
I can read it if you can't find it.
Oh yeah, sure. That'd be great.
Okay, so the question is, for derived implicit instances in Magnolia, if I do an IntelliJ implicit search, will I get an explanation of how Magnolia was able to derive it, or is that elided due to the macro?
I don't think it works with IntelliJ, but Magnolia, starting from one of the most recent versions, like 0.12, 4 or 5 actually provides very nice error messages if it fails to derive something. It can pinpoint which field or which type it failed to derive.
That's cool.
Yeah, that's pretty cool. It's in one of the recent versions.
I guess I have a question as well. Have you looked at Scala 3's type class deriving and how that would differ from your approach?
Not yet. I'd love to, but because of the nature of our data pipelines, most of the stuff we do is pretty tied to 12 for now, maybe to 13 at some point. But I don't have plan to move to Scala 3 at any time soon because of all the ecosystem dependencies.
Yeah, of course, of course. Okay, cool. Well, thank you so much, Neville, and thank you, Claire.